I want to start by thinking about this problem that we partially did last time, and I want to do it in a general setting and tell you what's really going on here. So that's what we'll start with today. Any questions so far of any sort? Okay, you can interrupt me at any point and ask me a question in chat or just by unmuting yourself. So the question asks us to think about delta S system and delta S surrounding. Together, they are called as delta S total or delta S for the universe. It wants us to think about it for a process happening in two ways. The first one is isothermal expansion of an ideal gas from some volume Vi to Vf. So let's first tackle this one. This is what we had started last time, and let's see how to work through this. So again, the keywords here are isothermal expansion, isothermal, ideal, and the volumes have been given. So how do we proceed? It's a best way to start always is to write down first law of thermodynamics and then see what we can say about different terms. Delta U is equal to delta Q plus delta W. We can't say much about delta Q, and I want to drive this through your heads that just because it's isothermal, it doesn't mean delta Q is zero. This is a mistake many of you have been tempted to do many times. No, there is no connection. Isothermal means temperature is constant. That's all it means. It doesn't mean anything about anything else. However, now we have an ideal gas, and we know for an ideal gas, isothermal means delta U is equal to zero, because for an ideal gas, the internal energy depends only on the temperature. So we have delta U is equal to delta Q plus delta W, or delta Q is equal to minus delta W, or in a differential form, delta Q is equal to minus PdV, because delta W is minus PdV, right? So this becomes PdV. Therefore, delta Q by T is PdV by T. And delta Q reversible by T, because that's what we are really interested in, calculating the integral of delta Q reversible divided by temperature over the process. That's the entropy change for our system. For this one, we can use the equation of state now, because first of all, we know what is the equation of state. It's an ideal gas. And secondly, we know the process is being carried out reversibly. So it stays in equilibrium.
Excuse me,
So
Professor.
in that case, we know PV is equal to nRT, or P by T is equal to nR by V. And that we can substitute over here. So P by T is equal to nR by V. So this is nR dV by V. Therefore, delta S system is the integral of dq, or let's be careful, delta Q reversible by temperature. And for this reversible path, using this formula, we can integrate nR dV by V. nR goes out, and we are left with nR ln Vf by Vi. And if the problem does not give you the ratio of initial and final volumes, but it talks about the initial and final pressure, well, it's an isothermal process. So changing the volume into pressure is, if Pf and Pi are given, you can use equation of state to change this equation into that, which I think is the case in this problem. The pressure is for one here, but the formula is the same. So that's delta S system. We need to think about delta S surrounding. What is delta S surrounding? To get delta S surrounding, we have to realize that heat gained by surrounding is equal to heat lost by system. And you have to be careful with signs here. Here we are talking about absolute values, but if you write it down rigorously, this means that dq surrounding, in this case, or delta q surrounding, is minus dq system, because the net heat change of the system plus surrounding has to be 0. Therefore, dq surrounding, and it's an isothermal process, the system, the surrounding has the same temperature as the system. Therefore, dq surrounding by temperature is minus dq system by temperature. And therefore, delta S surrounding is integral dq surrounding by temperature is equal to minus integral dq system by temperature. And we just calculated dq system by temperature. All we need to do is to put in a minus sign up front. Okay, there's Elizabeth had said it again, then Michaela said, no, it's okay, I found what I was going to ask. Okay, it looks like you guys sorted yourself out. If not, please interrupt. So, and this we just calculated over here, and this is the same thing with a minus sign, minus NR ln VF by VI. So now if we sum up delta S total as delta S system plus delta S surrounding, we get a 0. It's neither positive, it's neither negative. It's neither positive nor negative. And second law of thermodynamics told us that for a process to be spontaneous, the delta S total should be positive. So neither the expansion, this is for the expansion, nor the contraction is a spontaneous change. None of them is spontaneous. And that is kind of an obvious thing because we assumed reversibility to do all of this. The process was being carried out reversibly. That's why we could use the value for pressure over here from the equation of state. Otherwise, it wouldn't be true. And that's what we get here. For a reversible process, net entropy change is 0. System, is the sum only 0 for isothermal reversible process? It's 0 for a reversible process. You can go and try it out for isobaric processes, and maybe you will see a problem sooner or later where you should get the same answer. It's really the reversibility that matters in this case. But now let's look at a second case, which is, so you interpreted it and you see what's going on, it's reversible. Now you have to do A and B. And the only thing I've changed, I'm not going to post a separate solution to PB9. The only thing that is different in PB9 with respect to this problem is that you have been given actual numbers, but not for VF by VI, but you have been given numbers for PI and PF. You know how to do that just by using the equation of state over here. This can be directly converted into PF by PI. If you have doubts on how to do that, please post on Slack and someone will help you out. It's not hard. So now let's look at isothermal expansion. It's again isothermal expansion, but it's occurring freely into vacuum. So it's not reversible. You had a bunch of gas, you took it to outer space and you opened the container and you're allowing everything to expand. This is not reversible. You know, you can't just use so what changes here is our concept of surrounding. So let's work with this carefully. So this time the isothermal expansion is occurring freely into vacuum. So again, let's start with what we know, which is delta U is equal to delta Q plus delta W. It's an and since I forgot, it is again isothermal expansion of a perfect gas. If it was not perfect, then what we are doing next won't apply. We will have to think separately. It's isothermal expansion of a perfect gas. Once again, we can say delta U is equal to 0. However, this time, I can't say much about delta Q yet, but delta W is also 0. Because there is nothing to do work against. There is no surrounding. You're just expanding into vacuum. There is no work being done. Delta W is 0. Therefore, Q surrounding in this case, or let's write down Q system, delta Q is Q system is 0, heat given to the system. And once again, we should have Q system plus Q surrounding equal to 0. Surrounding is vacuum. And from this trivial argument, we can see that Q surrounding is equal to minus Q system is equal to 0. Nothing profound yet. Everything is 0. It's a bunch of zeros here. And now we can write down delta S total as delta S system plus delta S surrounding. And this is an interesting point where we have to be careful. What can we say about delta S surrounding given what we have written so far? It's 0, right? Nothing, no heat was given to the system, to the surrounding. There is no surrounding, there is no heat change. It's basically the way of thinking about it. There is no surrounding, it's vacuum. Delta S system at the same time does not depend on whether you took the path corresponding to 1 or the path corresponding to 2. Delta S, I will mark it in red. Delta S system is independent of 1 or 2. Does anyone see why? No one wants to help me.
Do we usually just define delta S as the delta Q reversible? Like if we were going to do the process
Abby,
reversibly? So it doesn't really matter which way, we just have to figure out what the reversible process like limits
Abby
are?
is speaking with great fervor, but I can't hear her. I imagine, Abby, you said it's a state function?
Is it working now? I don't know.
Just type it out.
Okay.
Like you can hear Abby? Maybe I was muted. Huh.
How about now?
Yeah, I can.
Okay. I'm not sure, but I was just thinking that because we always define delta S as just delta Q reversible over T, so it doesn't really matter. We just have to find a delta Q with the reversible limits. It doesn't actually matter if the process itself is reversible or not.
That's correct, but you know, so be careful here. Just because delta S is written as a reversible path divided by temperature integrated, that does not tell us on its own that all reversible paths will give us the same delta S, does it? It's not obvious.
Oh, okay.
Right? Why should that be the same? We haven't proven that yet. That's what we are going to do next. You saw it for the ideal gas that 3 of the paths gave it, but that's not a proof, right? That's an illustration why it might be the case. However, we have made a bolder statement that delta S is a state function, which is another way of stating that it won't depend on which reversible path you take. And that's why delta S system, thank you, Abby, I'm sorry, I was muted, annoying. So delta S system is the same as last time. Delta S system is nR ln Vf by Vi. So the whole thing is nR ln Vf by Vi. And now notice we have expansion. So Vf is more than Vi. Therefore, delta S total in this case is positive. Therefore, this is a spontaneous process as per second law of thermodynamics. And should we get the Nobel Prize for this? No, this is obvious, right? If you have a gas in a container and open it up to vacuum, it will expand. By the way, I hope all of you saw the Nobel Prizes in the last 3 days. This morning was given for CRISPR technology to Jennifer Doudna and Emmanuel Chantinier. So 2 women winning the chemistry Nobel Prize. It's very impressive. And it's not happened many times. Also for a technology which has definitely affected everything. And yesterday was Roger Penrose and 2 other people for Roger Penrose for his theoretical work on black holes. Stephen Hawking would have won it, but he died, right? So also Stephen Hawking is probably above Nobel Prizes. And
Professor, I have a question about what you just did. So just making sure, you said Vf is greater than Vi just because it's in vacuum, so it expands in vacuum? Okay, thank you.
Yeah. And the first one was Chemistry Nobel Prize. Did anyone see what that was given for? Sorry, the Biology Nobel Prize. Did anyone see what that was given for 3 days ago? It was for discovery of the hepatitis C virus. So in a strange way, both chemistry and biology Nobel Prizes are biochemistry oriented. So for the biochemists in the audience, you have a chance of winning 2 Nobel Prizes. That would be super cool. I don't think anyone has ever done that, to win the biology Nobel Prize and the chemistry Nobel Prize the same year. If you do that, I will be very proud. So that's all we saw. We just saw something obvious, that if we have a gas in a container, gas molecules in a container, and we just open this up to vacuum, the gas will spontaneously try and take up all the space in the vacuum that it can, right? And it's not going to come back. However, if you have the same gas in a container and you have a pressure being applied here, it's possible to do it reversibly. In this case, the gas could expand, it could go up, or it could go down. Both processes would be possible. And that's the difference that we saw. So that's some more introduction to entropy. This delta S total is an important concept. And after midterm, when we meet, we will be revisiting delta S total in many different ways. Delta S total is what directly leads to these concepts of which you might have heard the name of, called Gibbs energy and Helmholtz energy. They are nothing but a restatement of something related to delta S total. So what I'm going to do next is to work through a proof of why entropy is a state function. Yeah, that's what I'm saying. Delta S for path 1 and path 2 are equal because it's a state function. Because delta S does not depend on path. So you can have any amazing path, any complicated path, it just wouldn't depend on it. You can go from pressure from this point to this point. Okay, let's do a little, not a pop quiz, but I want to see if this point is clear. Let's say this is a PV diagram and I drew a path like this. And let's say I draw another path like this. And let's say I have one path which looks like this. There are 3 paths, 1, 2, 3. Is it possible that any of these paths is irreversible? Is it possible even? Or do all paths have to be reversible if you have drawn it in a PV diagram? So to answer this question, it is possible to draw irreversible paths even in a PV diagram. It's just that whether the pressure at this point is coming from the equation of state or not, right? If it came from an equation of state, then it has to be a reversible change, or equation state won't apply. So just because a path looks complicated doesn't mean it has to be irreversible. It could still be a reversible path. And what we are saying is internal energy U, enthalpy H, entropy S are all things that do not depend on what path you take. These paths could be reversible, irreversible, as different, as complicated as you wish. The change in U, H, and S will be the same for all of them. So before I move to showing that this is really true for entropy, we have seen why it is true for U and H. Have we seen why it is true for the internal energy U? Does anyone want to think about it? Why is internal energy a state function? Did we prove that? If you're really careful, we did not prove that, right? Because the way we introduced internal energy was to say, if we defined it through the first law, right? It was almost defined. We said, there is heat given to a system delta Q, which is some path function, no claims about it. There is some work done on the system delta W, path function, no claims about it. The sum of these two must be a state function. That's first law of thermodynamics. And this state function is called internal energy. So that's how we saw that internal energy is a state function. We defined it that way. H at the same time was U plus PV. H was a state function because taking a state function and adding two state variables or state function to it will still keep it a state function. Nothing has changed. Entropy, however, is hard to do that. Entropy, we haven't yet defined. It's not as simple of a definition as U plus PV. If you go with the molecular definition, then maybe it is a state function, but at least in a purely thermodynamical sense, we have defined entropy as the change in going from some path, some state A to some other state B, and looking at delta Q reversible. So it's not obvious at all as to why this should be a state function. We looked at for an ideal gas. That is not a proof that it is a state function. We looked for an ideal gas. We had many ways of going from point A to point B. We had an isothermal process. We had an adiabatic process followed by an isochoric process and a bunch of other things. And we saw that all of them gave us the same change in entropy going from A to B. So that's nice because it illustrates it might be the case. But first of all, these are just specific paths. This doesn't say anything about this path, for example. And secondly, it is only for an ideal gas. So how do we do it in general? So in order to do that, we are going to follow a recipe. And the recipe involves a very special type of path, which is called a Carnot cycle. So before we go into Carnot cycle, let's see what is it that we want to prove. We want to prove that entropy is a state function for any material with lots of complicated interactions. It could be even a quantum material with long-range interactions or whatever you want. It's any material. So for this, we want to prove that entropy S is a state function. What does that mean? We want to prove that the integral of dq, or I should be careful, delta q reversible by t between any two states is independent of the path between them, not just for an ideal gas, but for absolutely anything. So to do so, it is sufficient to show that this integral, that is integral of delta Q reversible by temperature. So we want to show that if given 2 points A and B, it does not depend on the path you took between them. And what I'm claiming next is it is sufficient to show for that this integral along any arbitrary cycle is 0. So there are two statements I made here. First was that I want to calculate it from some point A to point B in a PV diagram or a PT diagram or whatever, going from here to here, and show that irrespective of whatever path we take, it's going to be the same. The second statement, which I'm saying, is that these two things are equivalent, is that if we took A and B as the same point, A is equal to B, then if we design a path that comes back over here, and it could be any path, any complicated cycle, all of these would give the integral of entropy. So I drew a circle on my integral. Equal to 0. So these two things are equivalent. And we are going to work with this one. So this will be done in 3 ways. I don't think we can finish all 3 of them today, and it gets progressively more abstract as we work through these 3 steps. So we will do this. So let me summarize. What do we want to do? We want to show that integral of ds along any arbitrary cycle, which is when a and b are the same points, that is equal to 0 for any arbitrary cycle. So basically, they are just saying that if you come back to the same point, whatever path you take, your entropy is going to be the same, which is exactly saying state function. The point defines what the entropy is. Doesn't matter what you did in order to get there. It's not same for heat, right? You could have a path where you start from this point over here and you make some complicated path. Let me draw it with a red line, and you come back to over here. Why should heat be 0 along this path? Heat can be completely something else. You came back to the same point, but doesn't mean that doesn't necessarily imply that the heat transferred to the system is 0. It could be something non-zero. But for entropy, it will always be 0. So it's defined uniquely by the point that you started from. That's it. So we want to show that it is true for an arbitrary cycle. So we are going to do it in a 3-step process. What are the 3 steps? The first step, we are going to show that it is true by it. Let's call it equation number 1. That's what we are trying to prove. And step A in our 3-step process, we will show that this is true for a very special cycle. We won't do it for all cycles. You know, in the previous picture, I drew arbitrary cycles. So I'm saying first, let us prove it for a very, very special cycle of moves in PV diagram, which is called a Carnot cycle. T is silent. I saw a joke recently, which was quite funny. I thought this reminds me. I think Carnot was French. So it was a meme where someone had a book which was this thick, and it said, "My novel in French, as is." And the second picture on the right was the book was this 1/5 of the thickness, and it said, "My novel in French with all the letters that are not pronounced removed." And then the novel had shrunk to 20. So if you have taken French or tried to learn French, you know what I mean, right? So T is not pronounced. Thank you, French people. Sounds about right, yeah. It's not the same in Italian. I have a vocabulary of 2,000 words in Italian, and it was way easier to pick up than French. So we will show it that it is true for a special cycle for a perfect gas. And I will draw that cycle and show you what it is. First, we will prove this. Then we will use this proof to show that it is true for Carnot cycle, that special cycle, for any gas or any material. And that's an interesting proof. There we will take an engine which is doing work and try to run it in the opposite way and couple both of them and show how it works. And the third one, which is simple but kind of abstract, is to finally show that 1 is not just true. So in the first, we showed that 1 is true for special cycle for a perfect gas. In the second, we are going to show that 1 is true for Carnot cycle, that special cycle for any gas. And in the third one, we are going to show that 1 is true for any cycle for any gas. And that's our proof of showing that entropy change is 0 along arbitrary any cycle. So I'm going to talk about the first one today. I don't think I will have time to get into second one. Let's finish the first one. Let's introduce you to Carnot cycle. The other reason I'm doing this is because this manipulation is similar to the type of things we are doing already and you will probably be doing in the midterm. By the way, the midterm will be released tomorrow morning. you can ask me direct messages on Slack if you have a problem about any question. Please do not post messages about the midterm in general channel or any of the channels. We will be deleting them right away. If you have a question about the exam, do you really think this makes sense? Is this wrong? Is this right? Post them in a direct message to me straight, and I will respond to you. Most likely I will respond, it's exactly right. If there is a mistake, then I will announce it to everyone through Slack and through email. And since the exam should not take more than 2 hours, it should probably take less. You will have enough time to go back and change things. It will be released tomorrow morning. It will be due Monday. And you can do it in as many settings as you want. You can use whatever material as you want. If you have bought a solution guide to 5 different books, you can open them also. You're not gonna, it won't help you tremendously, but you can try whatever you want. You can use whatever book you want. I really don't care. For the math parts, you can go and type in things on the Wolfram Alpha and just write down the math. That's also totally fine. But there are at least half of the problems that will require you to think. At least half of the problem are, how to say, copying proof. You will have to think through. You can, however, copy from each other, and that's something which is not allowed. You are not allowed to talk to each other about the exam. It is your exam. You can talk to it. There is an embargo on the talking, which will be lifted Monday morning once everyone has submitted. Until then, just because you have submitted, you cannot go and ask your friend, hey, did you do problem 2? How was that? Please don't do that. And if you have any questions, just send me a message on Slack or on email, and I will respond quite quickly. So let's work with step A. So what is this Carnot cycle? The Carnot cycle is something that was devised by Sadi Carnot, a French engineer somewhere in the 18th or 17th century.
Professor, I think your screen is frozen.
Yes, it did, but I didn't draw much, so nothing lost. Okay, so we are going to draw a Carnot cycle, and this is how it looks like. So we have a PV diagram. It can be drawn on a PT diagram also, and this is going to be one of your problems on the 4th homework. I won't do it in midterm, but to draw the Carnot cycle on a PT diagram, it's a good exercise. So we have 4 points here, A, B, C, D. And we start from A, we take an isothermal path to go to B. From there, we take an adiabatic path to go to C. Now I have started writing. I wasn't writing much, so it's not that your Wi-Fi was too horrible. I wasn't writing much, but now I am, so you will slowly see. Then from here, you take another isothermal path and another adiabatic path. So we have here point A, B, C, and D. This is our first, we start from A to B along path 1, from B to C along path 2, from C to D along path 3, and from D to 4 along path 4. So this is, the screen is black, that's sad. So this is a specific cycle. This is called a Carnot cycle. And this one over here is an isotherm. This is also an isotherm. And so far we are doing only for a perfect gas, okay? This one is an adiabat. And this one is also an adiabat. So and this is path 2, this is path 3, this is path 4. So our cycle is made up of 1, 2, 3, and 4. Out of the 2 isotherms, how about you log back out and come back in, Michaela? That might work. Okay, if you get stuck in the waiting room, we will admit you. So out of these 2 isotherms, one is at a hotter temperature TH and one is at a colder temperature TC. Which one is at a hotter temperature, 1 or 3? What do you all think?
Can you say that again?
Out of 1 and 3, which one is at a hotter temperature? 1 or 3? One of them is, both are isotherms, right? So why 1? Everyone wrote 1, lots of ones. Anyone want to explain why? You're saying that 1 is at TH, hot temperature, and 3 is at TC, cold temperature. Why? How do you know that? Just by looking at this.
Since P times V equals nRT, if the P times V is greater than N and R are assumed to be constant, so
Yeah.
T has to be greater.
Precisely. That's correct. So if you're drawing a curve, xy is equal to 1, if it looks like this, then xy is equal to 2 will look something like this. It will be above xy is equal to 1, right? And this is x is p, y is v. So in the midterm, there will be at least one problem where I will ask you to draw such a curve. I will describe a process to you, and you will have to construct a cycle. Or it might not be a cycle, it might be a non-cycle path. And this type of reasoning as to which one should be lying higher, which one should be lying lower, try to become comfortable with it. It's harder for a van der Waals gas, but you will be doing it. You have to use, if it's an ideal gas, it's easy to think through. If it's a generic gas, you still might be able to come up with arguments, but this is an important type of reasoning. So one is, let's write this down separately and cleanly. So one is isothermal at TH, 3 is isothermal at some cold temperature TC, and 2 is an adiabat, 4 is an adiabat. This very special set of moves is called a Carnot cycle. It's very, very specific. It's, you know, it's like, yeah, it's very, if it has to be in this order, well, it's a cycle, so the order doesn't matter, but it's isotherm, adiabat, isotherm, adiabat. And you can see Atkins talks about it physically, what this means. You are taking, yeah, we will get into the physical interpretation, but let's write down 1, 2, 3, 4 in a bit more detail. So what is 1? 1 is isothermal. It's not just isotherm, it's also isothermal expansion, right? If you look at the volume, as we went from A to B, it went up. The volume here went up. So A1 is isothermal expansion. And I forgot a very important word which will make our life much simpler, which is isothermal reversible expansion. Why do we care about reversible? Because we know that entropy is defined as delta Q reversible. So we are not interested in irreversible paths anyway. So this is isothermal reversible expansion at T is equal to TH. 2 is adiabatic reversible. Again, it's expansion, right? The volume went further from B to C. But the temperature will change. 3 is isothermal reversible contraction at T is equal to TC. And 4 is adiabatic reversible contraction. If you look at 4, the volume went down, right? From D to A, the volume went down. Reversible contraction or compression at some as the temperature changes. So the idea in all of this was that you can get work out of this cycle. You are taking, you have a process. How does an isothermal process happen? Every step is reversible, right, Abby? Everything is reversible. Nothing is irreversible in this. So you have a process happening in contact with a hot reservoir. You take a gas and you put it in contact with a hot reservoir. What does that do to the gas? The gas expands. And then you allow the gas to contract in contact with a cold reservoir, and you connect this with two adiabats. And so in a way, you are taking heat from a hot source and giving some of it back to a cold source and trying to take the difference between the heat that you took from the hot source and the heat that you gave to the cold source to get some work out of this. So the net thing out of this is you should be able to get some work out of this. You should be able to drive a car or a steam engine or something like that. That's what Carnot was trying to do. We will talk about the work done, but right now let's focus on proving our step A, which is the entropy change along this cycle is 0. How do we do that? So we have to calculate delta S system. And again, remember, we are talking about entropy as a state function for the system, not for system plus surrounding. Okay? So did your screen work, Michaela? I saw you logged back in, or you're there. Hopefully it worked.
Yeah, it worked. Thank you.
No problem. So we are not talking about delta S surrounding. We are talking only about delta S system. We are talking about the state function entropy for the system. So to do this, it will be delta S1, delta S2, delta S3, delta S4. Which of these 4 can we knock out immediately?
2 and 4,
Why?
because they're adiabatic.
Precisely. So this is going to be delta S1 plus 0 plus delta S3 plus 0. So adiabatic processes are complicated for a variety of things. But for one thing, they are wonderful, which is entropy change. There is no heat transfer, entropy change is 0. Because it's reversible adiabatic. If it was irreversible adiabatic, that's another story. But it's a reversible. So because we have a reversible adiabat going on. No, so now we need to calculate delta S1 and delta S3. What can we say? Let's say this isotherm took in heat QH into the system. And let's say this isotherm gave out heat QC, okay? Because the gas is expanding in 1, so it took in some heat in order to expand. So I'm saying QH is more than 0 and QC is less than 0. I have defined it this way. So given these two pieces of information, what can I say about delta S1 and delta S3? Can I write them down? Why would there be heat transfer if it was irreversible? I thought adiabatic means Q is equal to 0. You are absolutely correct, Noel, that there won't be any heat transfer if it's irreversible. But my point is that it's irreversible, right? So even if the Q is 0, it's not useful for you to calculate entropy change because the entropy change wants you to calculate heat in a reversible process, correct? So you can't use it. It becomes useless. That's all I'm trying to say. You're absolutely correct. There is no heat transfer, but it's useless for our purpose. So hopefully it helps you. How about delta S1? It's step 1 is a process that happens reversibly at a temperature TH and the heat change is QH. Can we write down delta S1? Let me help you more. Delta S1 is integral A to B delta Q reversible by temperature. How much will this be? QH divided by something? By T. And the TH, right? So the nice thing here is that it's an isothermal process. It is going to be A to B delta Q reversible divided by TH because temperature is kept constant and that can be taken outside 1 by TH, A to B delta Q reversible. And now we know that is QH. So this is QH by TH. Similarly, for delta S3, it is going to be QC by TC. And I have left QC negative. So like, Natasha, I hope I pronounced your name correct. You asked a good question and I want to engage you here in order to answer your question. You said one would be spontaneous when the other is not. Good question. Do you really think we can say that currently on the basis of this entropy? So clearly this one is positive, this one is negative. Does that allow us to say that one is spontaneous and the other is not? I want Natasha to answer. You can just type in chat, Natasha, or unmute yourself. No, it's not about the enthalpy. What we don't know is delta S surrounding. We haven't calculated that. And that's the whole argument, my favorite rant in PChem about using second law of thermodynamics to deny evolution, because you have to calculate the change in entropy of the surrounding, of the sun, of the universe, and everything else. We haven't done that, so we are not in the basis to say that. You might be able to do it. You can go and do the math we did at the beginning of this class and find that, oh, it is actually spontaneous or not. But just on the basis of what we wrote over here, we cannot say that. Okay, because second law talks about delta S total. This is a word that please drive it in your head. This delta S total is always delta S system plus surrounding. In many of these problems, we calculate delta S system. That's not sufficient to tell us about delta S surrounding. So we have this. Now we need to calculate QH and QC. We don't know what they are. So again, in order to calculate QH, what is happening? It's an isothermal process, right? So let's write down our favorite equation, first law of thermodynamics. Isothermal process for a perfect gas. Therefore, left-hand side is 0 is equal to delta Q plus delta W. Therefore, delta Q is equal to minus delta W. Therefore, QH is integral of PdV. And now we can use our equation of state, and this will be nRTH ln VB by VA. I did it in a line, and I would really request you to be able to do this in a line yourself, all of this. This maneuvering should be trivial to you. I know it is already trivial to some of you, but the others also, if you practice for this, going from here to here for an isothermal ideal gas, isothermal process for an ideal gas, why should be the heat transfer nRTH ln VB by VA? It should be, you should be able to do that in a jiffy. And I think you can, because the key idea here is the U is 0. So delta Q is equal to minus delta W. Delta W is minus PdV. And now, since it's a reversible process, we can use the equation of state and get the integral. So QH is nRTH ln VB by VA. By a similar argument, QC is nRTC ln VD by VC. So we are running out of time, so I won't be able to finish all of this today, and that's okay. We won't be asking you anything about the Carnot cycle on the exam, so don't worry about that. But as a practice problem for the exam, so far we have seen QH is equal to this thing, QC is equal to this thing. I would like you to use QH, QC, and also prove that Vt to the power C is equal to constant for adiabat. We have done it last time, right? So prove that Vt to the power C must be equal to constant for AD and BC, for both of them separately. Use both of them to show that QH by TH plus QC by TC is indeed 0. This is a wonderful practice problem that I would like you to think through. Once you do all of this, it connects a bunch of things and you will feel comfortable, hopefully, after doing this. So what this amounts to showing is that we have QH, right? QH is NR, TH, ln VB by VA. So we want to show that NR ln VB by VA plus this one, NR ln VD by VC is equal to 0. That's what you need to show. Yeah, absolutely. Please post it on Slack. Absolutely. Or, yeah, I'm giving you too many hints. Just try to do this. The key thing here would be to be very familiar with doing this. Once you do this, it's not hard, and you should be able to show that this. Once you do this, what have we shown? We have shown that delta S1 plus delta S3 is equal to 0. And we already know that delta S2 and delta S4 are 0 because they are adiabats. So this means that all 4 are 0, or delta S Carnot for a perfect gas is 0. Once we do that, our next step would be to show that, so this is later after midterm. Don't do this in your practice. You can, but it will be a bit complicated. Then we are going to show that delta S Carnot real gas is 0. And then we will show that delta S real any cycle is 0. And that's the real thing that we want to show, which will show us that entropy is 0. So this we will do after midterm. So no class on Friday. And good luck with your midterms. And please send me direct messages or emails if you have any question. Try not to post in the general discussions in any of the channels because it will distract others. Okay? Good luck.
Thank you.